Hello everyone, it's 1 p.m. Eastern, and that means it's time to begin another of our monthly CoCoRaHS WxTalk webinars. Thanks for joining us today. I'm your host, Henry Regis, and joining our program today is CoCoRaHS founder and director Nolan Duskin. Behind the scenes running the technical side of our program are Zach Schwalbe and Noah Newman. We're coming to you live from the Colorado Climate Center here at Colorado State University in sunny Fort Collins, Colorado. For those of you who are unable to join us for a live broadcast, we'll be recording it for future viewing on our website. And all of our WxTalk webinars are sponsored by grants from NOAA's Office of Education and the National Science Foundation. Well, today's webinar, we're going to take a look at space weather. That's solar flares, the sun, solar wind, well, literally anything out there that's out of this world, that kind of stuff. We're excited to have with us today Rodney Viereck, and Rodney is currently the director of NOAA's Space Weather Prediction Testbed in Boulder, Colorado. That is where they develop new models and products to improve the accuracy and lead time of space weather forecasts. His areas of expertise include space weather, the aurora, and solar irradiance and its impact on the Earth's atmosphere and climate. Rodney recently developed a new real-time product for estimating where the aurora is. Rodney and his wife live at 8,500 feet, that's pretty high up there, in the small town of Pine Cliff just above Boulder. He is a CoCoRaHS observer himself and a big fan of our network. Rodney, welcome. It's great to have you with us today.
Thank you very much, Henry.
Hey, Rodney, I got a quick question for you. Would you mind taking a minute to tell us a little about how you became interested in space weather, and when was the first time that you saw the aurora?
Well, I was born and raised in Fairbanks, Alaska, and so I really can't remember when I saw the aurora the first time, but I certainly remember it growing up. And the way that I was I had a mentor when I was growing up, a neighbor who was the director of the Poker Flat Rocket Range. And so when I was a kid, I would get to go out and watch rocket launches. These are big rockets that would go up and study the aurora. So that was a fascinating way to be introduced to the science behind the aurora.
Wow, that's a great experience. I would love to have done that as a kid. Neat stuff. Well, go ahead and take it away with your broadcast today, with your presentation. We'll be back with questions afterwards.
All right. Yes, I'm Rodney Viereck. Thank you very much for inviting me to give this presentation. I'm with the Space Weather Prediction Center. The center is actually, if you're familiar with NOAA's structure, there are 9 NCEP centers, National Centers for Environmental Prediction, the Hurricane Center, National Hurricane Center, the Storm Prediction Center. Those are the 2 that are most well known, and we are the Space Weather Prediction Center. So our job is to provide the nation with alerts, watches, and warnings on space weather. Here's an outline of what I'll talk about. I'll give you sort of a what is space weather and who cares kind of presentation. And then in the second half, I'll talk about the aurora, because that's really the best way and the only way that you can really experience space weather yourself. So jumping right in, what is space weather? Basically, it's the variable conditions in the space between the Earth and the Sun that can influence the performance, reliability of space and ground-based technologies. It can actually get into situations where you put life at risk. So it's a pretty important subject, although not many people know much about it. In this space between the Sun and the Earth, there is electromagnetic radiation, there are energetic charged particles, there are magnetized plasmas or magnetic field, and as you see in this image, there's the Sun and the Earth. They are not to scale, obviously, but the Earth has a protective magnetosphere around it, which does shield us from some of the space weather effects in the solar wind, but not all of them. Briefly on time scales, just to show that the space weather occurs on everything from seconds to years, a solar flare can rise in a few seconds. It takes about 8 minutes for sunlight to get from the Sun to Earth. In 10 minutes to 2 hours, that's the average duration of a solar flare. 1 to 4 days is the time that it takes a coronal mass ejection. This is a big blob of magnetized plasma that I'll talk about. It takes about that long to transit from the Sun to the Earth. The Sun rotates every 27 days, and if there's an active region on the Sun, it will probably rotate back around and be facing Earth 27 days later, so a lot of space weather occurs on a 27-day period. but those active regions can last up to 300 days. And then finally, there is this solar cycle, and you may have heard of the 11-year solar cycle. The sun goes through its own natural internal cycles, and that lasts about 11 years. So right now we're just coming off the peak of a solar cycle. It's a fairly small one, but we're on our way down towards from solar maximum to solar minimum. There are three types of space weather storms. Just like terrestrial weather, there are different kinds of space weather. Like you can have solar flares, which actually cause radio blackouts, and so I'll talk about those. Energetic protons, those are ionized hydrogen. They can be accelerated to high speeds and cause radiation, so we call those radiation storms. And then, as I mentioned, the coronal mass ejections, those are these big blobs of material that you can see in this image, sort of this coming off of the sun, and those produce the geomagnetic storms. The aurora is associated with the geomagnetic storm, the third one of these types of space weather. Here's just a brief outline of our Space Weather Prediction Center. We are in Boulder, Colorado. We've been in existence in one form or another since 1946, when they first invented radio communication. They recognized that solar flares and affected radio communication, and so that's when the Radio Propagation Lab was first formed, and we've been in existence ever since. We now have a Space Weather Forecast Center. You see a picture there, 24/7. Forecasters are manning it. We provide specifications, forecasts, watches, warnings, alerts, just like terrestrial weather, and I'll talk about a few of those. Most of our products go out over the web. We have millions of customers who access our web services. We have a lot of models that I'll talk a little bit about. And here are the primary customers, and these are the people that we communicate with most. I think the most important is the electric utilities. The electric power grid is susceptible to space weather. And this is obviously a concern because we rely very heavily on reliable, continuous electric power. And so this puts us in very high visibility. Because of that, FEMA, the Federal Emergency Management Association, now has become very aware of space weather and its potential impacts on the power grid. We also work very closely with airlines. The aviation industry is very much affected by space weather. Communications, that's HF radio primarily. The ham radios at those frequencies between about 5 and 50 megahertz, those are all impacted by space weather. And I think GPS or GNSS, the Global Positioning System, that's our biggest fastest growing customers, because people are using GPS for new things that you would never have thought of before. And then, of course, all the satellites, the billions of dollars of satellites that are up there, and of course NASA's manned space program are the other types of customers that we work very closely with. We've tried to condense these three types of space weather down into what we call our NOAA space weather scales. Just like you can get the different hurricane scales or tornado scales or even earthquake scales, we've tried to create something that the public can sort of put their arms around, because we can talk about things in a very technical way, but that often loses people. So we have scales of 1 to 5, the G scale for geomagnetic storms, the S scale for solar radiation storms, and the R scale for radio blackouts. And you can go to our website up there in the corner, and it gives you lots more information on it. But each one of these will come up if you were to look, for instance, at a G5, which is a large geomagnetic storm. This chart will tell you what systems are affected, what the index that it's based on, and how often you might observe this kind of event. So jumping right in, we'll go right through those three types of space weather. The first one is solar flares, and we call these radio blackouts because the solar flare, which sends out a large amount of X-rays, that X-ray radiation travels at the speed of light and reaches Earth in about 8 minutes. It's detected by the sensors on the GOES weather satellite. NOAA flies weather satellites, and we put space weather sensors on them. There's the X-ray sensor and the solar X-ray imager. Those two sensors detect the solar flare. At the same time, almost instantly, the solar X-rays will modify the ionosphere, which is just at the top of our atmosphere at about 100 kilometers. And it will enhance the density. And of course, the ionosphere, if you're a ham radio operator, you will know that's the reflecting medium that allows you to communicate long distances with your HF radio, but if you start modifying the ionosphere, you're going to modify that transmission path, and you can block HF radio communication. Of course, the airlines use HF radio as their primary communication. They do have satellite radio for backup, but that's their primary one. And of course, ham radio operators, DoD still uses HF as their very dominantly in their operations, and this will also affect satellite communication. So when the ionosphere is disturbed, even the radio waves that transit through the ionosphere will be affected. Here's an example. So I'm going to play a little movie here. I hope you can see it. This is from the solar X-ray imager, and you see the active region on the left, and if you watch it, it will flare. And that shows you how bright the X-ray is compared to the rest of the sun in that wavelength. These are X-ray wavelengths, way shorter than what the eye can see. When those X-ray photons hit the ionosphere, I'm going to play this other movie. This shows where HF radio communication is blocked. So basically, underneath the sun, we call it the subsolar point, HF radio is completely blocked for periods of minutes to an hour or two. This is a product that we have that we put out to allow people who use HF radio to know when and where their communications will be blocked. As I said, the airlines who are using HF switch to satellite phones. That's usually based on a geosynchronous satellite, so they can quickly pick up communications again. However, in San Francisco, for instance, this is the Air Traffic Communication Center. These are the guys who are communicating with all of the commercial airlines that are flying, say, over the Pacific Ocean. Obviously, when a flare occurs, they immediately lose communication. There's no other sign of any problem, but they want to know very quickly whether there's a serious problem and they need to send out search and rescue, or whether it's just been space weather. So if you look at their operations center, at the front of the room, you'll see those two screens. The one on the left is that same product that I just showed you the movie of, our HF radio propagation product, because they want to be able to look up to that, instantly find out whether or not they need to send out someone to find a downed aircraft, or whether they can just switch to a different communication path using the satellite phones. The second type of space weather, solar protons. Now these are very energetic particles. They're not photons, they're protons, but they can still get accelerated by these solar flares and space weather events up to speeds of a third the speed of light. They can arrive at Earth in 30 minutes. And that a proton, while very small, still at that speed carries a big wallop, and it will penetrate deep into the electronics of a satellite, or it will penetrate into your skin if you're out in space and not protected by our atmosphere. One thing about protons is that they're magnetized, so they actually try and follow the magnetic field, and that's why the path of this particular, in this sketch, is curved, because it's trying to follow the sun's magnetic field on the transit from sun to Earth. But then as it reaches Earth and it's Earth's magnetosphere, you can see that it's funneling the particles down to where the field lines reach the top of the atmosphere at high latitudes. So protons, solar protons, penetrate the atmosphere, but only up at the high latitudes. Obviously, they have similar impacts on the ionosphere. They modify the high latitude ionosphere very much like X-rays, and they disrupt HF communication. The airlines will be affected. Again, the same HF radio operators and DoD. But the other thing that happens, as I mentioned, this is ionizing radiation, and it penetrates into the atmosphere. It also penetrates into satellites, and you can have satellite electronic failures. The astronauts are very much at risk. If they're out doing an EVA, an extravehicular activity, or a spacewalk, they are very vulnerable to energetic protons. And so when there's a big proton event forecasted, they will cancel the EVAs. Those same energetic protons can penetrate into the upper atmosphere, and there is enhanced radiation even at airline altitudes. Airline passengers and crew will get a little extra radiation, although not enough to cause significant risks. Here's an example. As I said, all these airlines are now using polar routes, flying across the poles from Los Angeles to Delhi, or from New York to Hong Kong. They go right over the pole. And normally they can communicate using HF radio, but during a proton event, they'll get that whole polar region where they can't communicate. Now you add the complication that inside this red circle above 82 degrees, you can't see the geosynchronous satellites. So now they don't even have satellite phone communication, and that means that they're not allowed to fly. So the airlines have to divert around the pole when there's a major proton event. Typically, they always run right up against their fuel limits, and so when you ask them to go around the pole, they actually have to either dump some of the baggage of payload, or they can stop in, say, Anchorage and refuel, but that often means picking up more. They have to get a new crew, because crews are not allowed to work beyond a certain number of hours. Typically, they say that for each flight that is diverted because of space weather, it costs the airline about $100,000. So this is not insignificant, and they really don't want to do that if they can avoid it. We provide them with a forecast. Now, proton events, unlike flares, which last only for a few minutes, proton events can last for days. And so this example at the bottom, for 3 days in a row, the polar flights were having difficulty with HF communication with air traffic control. So this is just an example of how the space weather can have a real impact on even the people who are just trying to get from one part of the world to the other. We have a way of tracking some of our high visibility customers, and this is just a partial list of all the airlines who sign up for our products and services, and this is pretty much a list of who's who in the airline industry. Satellite industry, obviously I've mentioned that their satellites are susceptible. The image, the little movie that's showing, is showing noise essentially on an imager, and that noise is from the energetic protons. They will turn off sensors. They will change their schedules for maneuvering. Sometimes when they have problems, they'll come back and do anomaly assessments. The Space Weather Prediction Center provides forecasts for these sorts of things for the satellite industry to try and help them mitigate the effects on their systems. Another system affected is the launch, and here, unlike a satellite where you can sort of let it, you don't want it to turn itself off, but you can sit and try and reboot it and get it to come back online. During the launch sequence, there's no opportunity to reboot things. Things are going too fast, and so launches are often canceled. I won't say often. When there's a proton event, launches are canceled because of the energetic protons and the potential impact they might have on the electronics on the launch vehicle itself. Here's an example of the first launch that was scheduled out of the Kodiak launch facility up in Alaska, had to be canceled because of a proton event. Then, of course, humans in space are the most vulnerable, and the impact is that the protons go in and actually break apart some of the DNA. And so NASA is very aware of this, and they will protect their astronauts. In addition, there are a number of other systems like the robotic arm, which are also impacted by space weather, and they will protect those sensors, those systems from space weather by turning them off and stowing them and putting them into a safe mode. The third type of space weather, and this is the one that has the most impact in some ways, it starts with a coronal mass ejection, or a CME, and that's the image in the upper left shows the CME, which is this big cloud of material, 1 billion tons of plasma traveling at 3 million miles an hour. Yes, that's a pretty good rate of speed, although even at those speeds, it will take about 1 to 4 days to transit from the sun to Earth. So that gives us quite a bit of warning. We see the CME at Earth, or at the sun, and then we wait for it to arrive at Earth. Unfortunately, we don't have a good way of measuring what's going on in between, so we can't see the evolution of that CME as it transits. It's somewhat like being able to see a large storm generated off the coast of Africa headed across the Atlantic, knowing full well that it might turn into a hurricane, but really not knowing anything about when it's going to arrive or how big it's going to be until it gets there. We have one satellite which sits at what they call the first Lagrange point, which is a place where the balances between the gravity and forces between Earth and Sun are balanced, and you can park a satellite there. That's the ACE satellite, or Advanced Composition Explorer. It gives us about a 30-minute warning. It's like having one weather buoy about 50 miles off the coast of Florida. When the hurricane hits, you get about a 30-minute warning that says, yes, the hurricane is here. And that's just enough time for the power companies to safe their systems and put their systems into a more secure mode so that they can survive the space weather storm. As I said, these geomagnetic storms, again, they affect HF communication, radio navigation. These are the ones that will affect the GPS system. So your GPS system will go from a normal, maybe a few centimeters error up to tens of meters. And in some cases, the GPS systems, the precise, what they call precision GPS, or those systems will actually lose lock altogether, and you won't have any positioning information. The other thing these geomagnetic storms impact are the electric power grids. All the accelerated particles that are traveling around the magnetosphere will then come down into the ionosphere, and they'll set up sympathetic currents in the power grid itself and will have a big impact. Also, the energy added to the upper atmosphere by these big storms will increase the density of the atmosphere, and that increases satellite drag. So satellite orbits become very unpredictable when there's a big storm. And then finally, the aurora. That's the way in which we can all see and experience space weather. Here are some movies of a CME. The one on the left shows the CME going off to the upper left, and that one is not headed towards Earth. But if we look at the movie on the right, the blue one, some of those are what we call halo CMEs, where they're shooting straight at Earth. They're not as spectacular to look at, but you'll notice in the image you see the stars, but then you see all the flecks. Those are the accelerated protons hitting the detector, and that's the noise that can also interfere with other types of electronics. Here's a movie. I hope you can see it. It's showing space weather. It sort of tries to capture all three of those at once, and we're zooming into the sun, and we're going to see a solar active region, a solar flare. Then you see the particles hit the detector right there. Now we'll zoom out and watch the CME propagate out away from the sun, and again hitting the detectors as the CME accelerates particles. And now we'll see the Earth view, and this is what happens when the CME actually hits the Earth's magnetic field. It reorganizes it, and then you get something called reconnection, which accelerates particles down the magnetic field lines to the top of the atmosphere, and that's what creates the aurora. So that was sort of a 30-second view of how space weather affects the aurora. We actually do have numerical models. This is a model of the solar wind. So the sun is the yellow dot. If you can see my mouse, I'm pointing at the sun, and we're looking down on top. You can see the sun rotating around. That's the background solar wind. Here's the CME being ejected out into the solar wind, and then you see it hit Earth, which is the little green dot. This model has provided a great improvement in our ability to predict the arrival time of some of these storms. So again, when we see the CME leave the sun, we want to know when it's going to hit Earth, and this model has provided us with that kind of forecast capability. Some of the customers for geomagnetic storm products include the GPS customers. Obviously, if you're doing surveying, if you see anybody doing land surveys and things like that, they all use GPS now. Any kind of topographic work or boundary analysis. Turns out now that farmers are using GPS. Their tractors all have precision GPS. They will plant the seed in one place one day, they will come back the next day, and the tractor knows exactly where every single seed was planted. It will come back and fertilize the seed, and then the following day it will put herbicide around the seed, and it'll water just on the seed. You know, they can really minimize herbicide, the pesticides, and maximize the value of the fertilizers by using precision farming using GPS. Road building, all the tractors and graders and things that are now building roads have GPS at the ends of each of the plow blades. Snow plowing and zero visibility is another place where GPS is being used. FAA, the Federal Aviation Administration, is now incorporating GPS into most of the aircraft, and especially during final approach and ground operations, GPS has become very critical. Zero visibility operations, GPS will become very, very important. And obviously, you don't want suddenly to go from a few centimeters of uncertainty to tens of meters uncertainty without knowing about it. So we work very closely with FAA. With DoD, we have joint operations with DoD. We contact them daily to make sure our forecasts are the same. Even things like deep sea drilling, where you're out there in the middle of the ocean trying to position your ship over a well. They need very accurate GPS. If they're out there and they can't get the accuracy, they say it costs them about $1 million a day of lost revenue if they send a ship out to try and drill during a geomagnetic storm. This is just, again, a list of some of the customers that are interested in GPS and precision GPS, and these people are all signed up for our products and services to try and improve their company's production. The impact on the electric power grid, as I said, the CME impacts the Earth's magnetic field. Those fluctuations generate electric fields on Earth, and that induces currents, ground-induced currents, into the power lines and transformers. This leads to transformer saturation, overheating, and then now you start having voltage drops and damage. And in the worst case, you can have a collapse of the entire grid. The vulnerability to the U.S., generally at northern latitudes where you have space weather and the Aurora, areas of highly resistive igneous rock. In other words, the ground is really important. If you're on one kind of rock, you won't get these GICs. If you're on another kind, you will. So we work closely with the USGS, who maps out the entire country in terms of what its ground conductivity is. Also, regions where you have lots of high voltage interconnects. That's a region of vulnerability. Proximity to oceans. Now, if you take all of those together, basically the northeast U.S. is the most vulnerable to space weather. If we look at a map, these are the power grid interconnects that are most vulnerable, and you can see obviously the New England area and the East Coast and the northeast part of the United States is the most vulnerable. The question is, what could happen in the worst case? What if we had a storm of not one in a decade, but one in 100 years or one in 1,000 years? How big could the impact be? And the concern is that those power transformers are huge. They're very expensive, and they're not sitting, they don't have spares sitting around waiting to be swapped in when one fails. When they fail, it's catastrophic. You actually destroy copper and burn up transformers. And so you can't just go repair it. You have to replace it. It may take months. And if there's a big enough storm that causes enough of these to fail, and there are no transformers sitting around as spares, you can have stressed power grid issues for weeks to months, and that's a big concern to, as I said, the emergency managers and others who are concerned about the reliability of our power grid. Fortunately, the electric power grid know exactly how to protect themselves from space weather, and they are one of our best customers in terms of knowing how to respond and keeping their systems from being affected. Here are some of the customers. Again, every major power company in the country signs up for our products and services. So we have a large customer base. It's evolving. It's changing. We go from just radio propagation to now even space tourism. We know that Virgin Galactic is about to start launching tourists into space. So all the issues that astronauts have to deal with are now going to be transferred to the general population, and people who can afford to take a ride in space are not going to be interested in getting extra radiation and being put at risk from energetic protons. So we're working again with FAA to help develop some of the rules and regulations associated with this new industry. Here's the list of all the kinds of industries that have signed up over the course of the last 60 years of our existence. And what's interesting is that most of them really haven't gone away. So we just keep adding new types of technologies that are impacted by space weather, and we provide them with the products and services that they need. The way we do that is we have a subscription service. You too can sign up. If you go to our webpage, you can sign up for email alerts, watches, and warnings. One of the things you have to do is give us your email address, and so we don't use that for anything other than tracking who our customers are, but that's how we learn who they are and what their interests are. Once you've done that, you can then choose what your threshold of pain is. You can sign up for an alert of 7, 8, or 9, depending on what your system is and how vulnerable it is to which type of space weather. And then you get products that come out, and there'll be email products that get pushed to you when there's a big event. We started this in 2005, and in the last decade we're now up about 42,000 subscribers. This is just a list of some of the more recent people who have signed up for our products and services. In addition to the major corporations, John Deere, Chrysler Corporation, satellite companies, we also have federal agencies like FAA. And these are all customers that sign up. On the other hand, if you were just to count the major corporations and companies and even the government agencies, it's very hard to get to 42,000. You might get 1,000 or two. The vast majority of the customers who sign up for our products and services are the general public, and they're mostly interested in the Aurora. So I'm going to switch gears and give you a little presentation on the Aurora. So this is part 2. The Aurora the term Aurora was first used by Galileo to describe the light. The Roman god Aurora was the Roman goddess of dawn. Borealis is the north wind. There's a similar one in the south called Aurora Australis. And I'll just tell you a little bit about the colors and shapes, cause, impacts, modeling, some forecasting that we're doing. The light itself, so when you see, if I go back one slide, this green, yellowish green glow is caused by energetic particles, mostly electrons, colliding with the upper atmosphere, the oxygen and nitrogen of the upper atmosphere itself. Now the collision energizes. If you go back to your physics or chemistry, you can energize the energetic state of an atom or molecule, and quantum mechanics says that atom or molecule will get excited to very specific energy levels, and when it relaxes back to its ground state, they release a photon of light of very specific wavelengths. So we can tell exactly what this is a spectrum showing the spectrum of the Aurora, and showing each of those wavelengths is a transition from one energetic state to another of one of the molecules or atoms of the upper atmosphere. This is exactly the same physics that goes on in a neon light. Neon lights are filled with neon and argon and xenon and these various gases, and you excite them and you get lights at very specific wavelengths, just like the Aurora. The most common color is green. This greenish yellow is at 557 nanometers. It's the most common and the most brightest, and it happens to be right in the visible range of our eyeball, so it's a good one for us to see. On occasion, you can get a very red aurora. These are less common, but they're often associated with very large storms and very much more associated with low latitude aurora. So when you're down here in the United States, you would more often see red aurora than you would if you were up. When I was growing up, I don't ever remember seeing a red aurora. But then once you get down to the lower latitudes, you start seeing them more and more. It's also associated with lower energy particles. Then on occasions, you can get very energetic particles which penetrate even further, and you can see the blue tinge at the bottom of these auroral structures, and that's a different, this is now nitrogen, and you can get these kinds of colors in the aurora as well, and again, as I said, they're associated with higher energy particles. And then in really special cases, you can get a purple aurora, and this is actually usually at the tops of those rays. But what you've got now is sunlight hitting the aurora and exciting that the same particles that have already been excited to one state get excited to another state by the photons from the sun itself. So this is a kind of an unusual phenomenon of electrons colliding with the atmosphere, exciting something to one state, and then photons from the sun hitting it, exciting it to another state. It's a little less common, but you can see in this particular picture the setting sun in the lower part of the image, indicating that the sun is not so far over the horizon. And the aurora itself goes very much very high into the upper atmosphere to 1,000 kilometers, so it's being illuminated by the sun itself. Here's some images of the sun, or of the aurora, showing different colors. We've got the reds and the greens, and here you see the red on top. If you look straight up, you often get these sort of starburst patterns because the aurora is actually following the Earth's magnetic field lines. And so what you see in those kind of streaky lines are actually, that's the direction of the magnetic field. And what you're seeing in this image is we're looking straight up towards, in the middle of the image is where the field lines disappear. They all come together through perspective. Another image of the same sort. showing multiple colors. In these images, you can sort of get a feeling for how bright the aurora is by comparing to the background star field. You can see the stars in the left side of the image, but then over on the right, the stars pretty much disappear because the aurora is about as bright as some of the stars. In this image, you're seeing aurora, but you're also seeing clouds in the foreground, which are basically, you're seeing the aurora behind those clouds. The aurora comes in a number of different shapes and forms. There are arcs, patches, bands, and rays. Each of them is associated with a sort of a different kind of physics, but if you look at the sequence over a night, if you were to sort of watch the aurora all night, you would first start with a quiet arc that goes sort of from horizon to horizon. In this case, you see the arc disappearing over the horizon. You also see some of the purple at the top of that arc indicating that it's just after sunset, and you're seeing that sort of just started evening time quiet aurora. And then as evening goes on, those arcs, sometimes you get a pair of them, will start to ripple and change. You can see the transition from the left image, and then a few minutes later it starts to kind of wrinkle or curl, and then things really get exciting and you fill the entire sky with arcs and bands and little patches of aurora. More arcs can form and literally go from horizon to horizon. Here's a photograph from space that gives you a perspective of the aurora. As I said, the red itself can go up to 1,000 kilometers. So the top of the red part of the aurora is about 1,000 kilometers. The green, which is usually much lower down, goes up to about 500 kilometers. And then the bottom edge of the aurora is more like 100 or 120 kilometers. And below that, you can just see sort of this layer, which is more constant. That's actually air glow as part of the natural chemistry of the atmosphere. So where do you need to go to see the aurora? This is often one of our most often asked questions. The aurora forms a ring around both magnetic poles, and it's actually symmetric. So when there's big activity on one pole, then you will see big activity on the other pole at the same time. Often, though, one pole is in daylight and the other is in darkness. So the more active the aurora is, the further south it will go. So that the oval itself gets larger and more bright as the auroral activity increases. It's also brightest right around midnight. So if you're looking at the day side of the aurora, it's usually just a very faint arc, but all the real excitement and activity is on the night side. Here's the globe on the right shows how often you would see aurora given at different latitudes. And so Fairbanks, you see about 100 aurora a year, but if you go down to Seattle, you might be able to see 10 aurora per year. And then from San Francisco, you'd be lucky to see one. And there have been cases where aurora has been seen as far south as Florida and Mexico, but those are very, very rare. When there is good aurora, you can see it pretty much everywhere. This is a storm that occurred back in 2011, and these are just some of the photographs that people sent in from various states. And so you can see pretty good aurora, even from as far south as Oklahoma and Arkansas. And again, you see that it's often very red, and that's again associated with these low latitude aurora. Here's another map. The aurora, one measure of geomagnetic storms is called the K index, or the KP, which is the planetary K index. And it just measures the size of a storm from a scale of 1 to 9. But the bigger the storm, the brighter the aurora, and the further south it goes. So we have an index and we have a forecast of KP, and based on that you can use this map to identify how big the KP would have to get so that you could see the aurora from where you live. One of the things that you can see here is that the aurora is actually centered not on the geographic pole but on the geomagnetic pole, which is somewhere up in northern Canada, which means that people in the United States get to see many more aurora than people in Europe at the same latitude. And so if you were to follow, for instance, you look here at about 50 or even 40 degrees north down here, in the middle of the United States where you could see a big aurora, you would have to go further north in Europe, all the way above 50 degrees to see that same magnitude aurora. So we're very fortunate in this part of the world to have the magnetic pole sort of in our direction, which allows us to see the aurora from much further south than you would in other parts of the world. So again, you go north. The further north you go, you see more aurora, although if you go inside the auroral oval, you might start seeing fewer aurora, but that means going very far north, and few people will venture all the way to the northern part of Greenland just to see the aurora. The other thing is you have to go in winter. I don't know how many times I've been asked from a customer, you know, they say, I'm taking a cruise to Alaska this summer, and I'd like to see the aurora. And I say, well, you won't see it, because most of Alaska is in sunlight or twilight all summer long, so there's just no darkness. You need darkness, so you have to go in winter. You also need clear skies, and so fall and spring are often cloudier than dead of winter, and it must be dark. You need to avoid cities, and the full moon can often degrade the experience. You can see aurora from space. This is a picture of the space shuttle, similar to the one I showed earlier. But you can also, here's another image. This is actually a movie taken from a satellite, the image satellite itself, and you can see a sequence of auroral substorms as this, each one of those brightenings of the aurora shows how the aurora sort of goes through ebbs and flows even over the course of this 5-hour sequence. And so you can imagine being there in Alaska right in the middle of the globe, and you would see the aurora very bright, and then it would flow, disappear, not entirely, but it would become much less active for an hour, and then it would brighten up again. And that's very typical of an auroral storm. You can go to Saturn to see the aurora. This is an image of Saturn showing the aurora on its southern hemisphere. Here's another sequence of images. Jupiter also has aurora. Many of the planets have aurora, and they're all caused by very much the same sort of physics that the aurora on Earth is, which is the particles colliding with the upper atmosphere. I showed you this image of data. This is measurements. We have a model that we produce which provides you with a 45-minute forecast of where the aurora will be. And if you go to this website here, you can see what our estimate of where the aurora is going to be in the next few hours. And this allows people to sit in their living room and wait until the aurora is more likely before they go out into the cold and the snow. I'll play that one more time, or not. So the questions, as I said, where can I go? Canada, Alaska, Scandinavia, Russia. You can even go to Antarctica. If you're very lucky, you can get a trip to Antarctica to go see the aurora there. Or you can wait for a very big storm. If you wait long enough, you will see the aurora just from your backyard. Again, this question, I'm going to Alaska, can I see the aurora? But you have to go in the winter, not in the summer. So this is the same list I just gave you. North, the aurora is usually brightest right around midnight. Winter, because you need darkness, typically away from the coast. Coastlines are often more cloudy with fewer clear nights. Away from cities is good because you want a dark sky. New moon is good. And then, as I mentioned at the beginning, the aurora, it comes from these active regions on the sun, and the sun rotates every 27 days. So you can, in a crude way, estimate that if there was some really good activity at the beginning of the month, then 27 days later, at the end of the month, you'll likely have good geomagnetic activity at that time as well. If we go back to the broader space weather, so now I'm stepping back from the aurora, and we're going to go back to as I wrap this up, we'll talk about space weather just a little bit more. Some of the other questions we get, one of the most often is, I'm pregnant, is it safe to fly? And our answer is yes. The radiation dose from one flight is not going to be dangerous, even if you fly during one of the more heightened periods of a proton event. However, if you are a flight attendant and you are pregnant, there may be some actual measurable risk. And in that case, most airlines will allow their flight attendants not to fly while they're pregnant, at least not those high-latitude routes that are most susceptible. Some of the other questions are, will my cell phone work? Yes, your cell phone will continue to work unless there's a severe event that blocks out one of the satellites itself, but there's no significant interference between the cell phone signal here on one tower and your cell phone and space weather. People hear about news reports of space weather storms and how that's going to wipe out the power for months at a time. Right now, we think that we've got a good handle on predicting space weather with enough lead time that the power companies that run the power grids know what to do and will protect our power grids from space weather. So this is obviously we don't know how big those storms can be. We haven't got enough data over enough time to know, but we do know that we have done what we can to protect our electric power grid. Of course, one of the questions is, does space weather affect weather and climate? And the answer is climate, yes. Weather, maybe, but it'll be indirect. You're not going to say, we had a big solar flare today, tomorrow's going to be rainy. There's no direct correlation like that. But if you look at this is just a model of climate, so you have global temperature in the top plot. The white is the observations. The orange is a model. It's an empirical model based on primarily 4 inputs. The purple here is the El Nino-La Niña oscillation. The blue is a volcano index, and then there's some small contribution to from the AOs and the SAOs, but if you look down below, you have a solar cycle in green and the anthropogenic in red. And each of these 4, all of these plots actually, are in scale with the anomaly that they produce. So if you added all those up, you would produce the orange line, and you can see that the effect of the sun, which is about 1 degree of temperature anomaly, helps improve the fit of the model. So yes, the sun does have an impact on climate. You're not going to explain global warming using solar variability, but you need to include solar variability to more accurately understand all of the other climate drivers. Sometimes we get some alarming stuff in the news, and this one just came out yesterday. Some of you may have seen it. It's a rather alarming title, How a Solar Storm Nearly Destroyed Life as We Know It 2 years ago. This was in the Washington Post. This is primarily NASA trying to make news out of something when things are very quiet. This is an event that's been in the news many times, and it happened 2 years ago. It just happens that this is the anniversary. But we at NOAA have to now temper people's response, because when you read those sorts of headlines, people start to get really alarmed and really upset, and we have to tell them, no, we don't believe that that's really true, that you're not going to destroy life as we know it. This has been somewhat sensationalized. However, the White House does read the newspaper, and so the president sees things like that and wants to know what are we doing about space weather. So we have very, very close relationships with the president's security advisor, as well as all of the federal emergency managers and Department of Homeland Security. They are all now experts in space weather, and they pay very close attention to our forecasts. Here's a list of all the emergency managers around the country that have signed up for our products and services, because they know that when things go bad, they will rely on HF communication, and HF communication is going to be impacted. Or perhaps they're concerned that their local electric power grids will go down, and they want to know how, why, and how long it will happen. So they're concerned, and they go through exercises to practice responses to space weather. And as I wrap it up, the FEMA director, or a representative of FEMA, we were training them, educating them on space weather and all the impacts, and he said, well, it would appear during a space weather storm that we'll have to resort to messenger pigeons as our primary means of communication. However, if you are a pigeon racer, you know that the pigeons use the magnetic field for their navigation. And if there's a big geomagnetic storm, those pigeons will lose their way. When there's a storm, they lose pigeons, and they will not release their pigeons before asking us about the current space weather. You may say, well, that's just a bird. Well, a breeding racing pigeon sells for about $100,000. You're not going to release a $100,000 bird into a conditions where you wouldn't release it into a snowstorm or a severe wind event. You don't release it into a geomagnetic storm either. So yes, you cannot rely on pigeons during major space weather events. So we have ever-growing dependencies on technologies affected by space weather, and that increases the need for space weather services. The health of the nation's technological infrastructure depends heavily on our understanding of the space weather and our ability to predict that hazard. And then finally, as I said, observing the aurora is really the only way to experience space weather, and many, many people in the country are now taking on that sort of the bucket list, if you will, of going north and seeing the aurora. And so we get lots and lots of people who are interested in space weather simply to go and experience it themselves. Thank you very much. And as I answer questions, I'm going to bring up a movie. I hope you can see. I'm going to skip the ad and bring up a movie of the aurora. This is actually, the reason I like this movie is that it's real time. So if you're, most of the movies that you see are time-lapsed or stop action. This movie may not be as vivid, but this is what the aurora looks like in real time. So this gives you a sort of a feeling for what it would be like to go north in the middle of winter, obviously, and see the aurora. Thank you all very much for your attention.
Rodney, thank you very much. We really appreciate some really interesting stuff there. You know, one thing it brought up a couple of years ago, we were heading to the airport, and we got lost. Everybody blamed me, but now I know my GPS was probably being affected by a coronal mass ejection. So
yes,
that gets me off the hook. Thank you for explaining that. A couple quick questions before we take our audience questions here. Are there other space weather centers in other countries, or are we the only one on the Earth right now? Are there others like you guys?
No, there are 14 countries that have stepped up with official space weather forecast agencies. There's an International Space Environment Services service that they coordinate their forecasts. We, the United States, are really the lead and provide most of the data and provide the most reliable forecasts. The Air Force, also recognizing that their systems are vulnerable, the Air Force Weather Agency in Omaha has a space weather operations center. So they too provide space weather services, but those are primarily directed towards the Defense Department and their needs, which are different enough that we don't have much overlap. We're actually quite complementary in terms of the services we provide. But even there, the NOAA and the civilian side of things provide most of the data, most of those images of the sun and the measurements that people use for forecasting and specifying space weather.
Okay, and we will put on our website some of the URLs that Rodney mentioned as far as how to sign up for these alerts and a couple of those things. So, if Rodney, if you could send those to me, we'll post those on our website here in the next couple of days. We've got a couple of questions that have come in right now. In fact, before we do that, let me give Nolan. I didn't give you time last time to ask a question. Do you have one for Rodney?
I do indeed, and thanks a lot for your talk. Would you let me know what how this latest solar cycle maximum compares with maximums of the past? I heard it was a really low one, but how low was it?
Well, the previous, one of the problems, of course, is that the space age has been during what they call the modern maximum, where there are 5 cycles that are quite a bit larger than the previous hundreds of years. So those cycles reached levels of 120, 150, those kinds of numbers, and that's the sunspot number that I'm quoting. This cycle, I think we're not quite far enough past the peak to give it the final answer, but we're looking at a cycle maximum of about 80 or 90, and you would have to go back to about 1920 to find a solar cycle that was as small as that. Again, this may be more average on the long term in the last few hundred years.
So folks that called this a non-event were overstating it.
Again, it's hard. Yeah, we would like to say that yes, this is an average cycle, not a small cycle, but it's small compared to the last 5 cycles, which are the only ones that we have really good space measurements during.
Hey, thank you very much.
Okay, let's take some of the questions that are coming in. We're getting a bunch. We're going to try in the next 20 minutes to go through as many as we can. Ruta writes in for Maine. She has solar panels on her house to make electricity. Will solar flares or protons impact that function?
No, not really. The sun itself is actually quite constant in terms of the photon output that transmits down to the ground. In fact, people used to call it the solar constant. The change in that solar brightness is really only 0.1%. So from the ground's if you're on the ground, the thing that will make the bigger difference is whether it's cloudy in the atmosphere or not. That will have a much, much larger impact. However, I will add a caveat that your solar panels are connected to the electric power grid, and if the power grid itself starts to have fluctuations and problems, then indeed you may become very popular, because if your solar panels can keep your freezer going, you may be the only one with good fresh food even after a few weeks of power outage. But that's, again, an extreme event, and again, I don't think there's any need to worry about your solar panels.
Okay, here's one from Gloria. Gloria has a two-part question here. A couple of things. Is the sun expanding, and is that why the Earth has been warming in the last few decades? And she also wants to know, is the Earth traveling through a very dirty part of space right now, more comets and asteroids?
Good questions. The sun is expanding, but so slowly that it'll be billions of years before we actually, the Earth is impacted in any major way. So over the course of our lifetime, no, the sun has not changed appreciably in terms of its size, but it has changed a little bit in terms of its brightness, and that will have an impact on climate. So yes, there are those who would like to argue that the solar variability, the increase in solar brightness, is actually causing some of the global warming that we've seen, but in fact, no. Most recently, the sun, as we mentioned earlier, Nolan was asking about this solar cycle. The most recent one is much smaller, so the irradiance is actually going down, and in fact, the climate is still warming. So the sun can't be used to explain the climate change of the past. Now, what was the second part of the question?
Is the Earth going through a dirty part of space right now? We have more comets and so forth.
I read about that. This is outside my field of expertise, so I really can't give an expert answer on that one. I did read somewhere that yes, we are in a dirty part of the Milky Way galaxy, but I don't know much about that.
Okay, here's Eric, and he refers to that Washington Post story yesterday, known as, I guess, the Carrington event. Can you talk a little bit about that, just what came out? And he says that there's a worry that something like this could happen in the next decade and so forth. Just if you could clear that up a little bit.
Yeah, so one of the biggest space weather events that has ever been recorded was recorded by Carrington, who was a sort of a solar scientist back in 1859, and he did not have sophisticated instruments, so it's really hard to estimate how big that was. There were some really remarkable impacts. For instance, while there wasn't a broad network of electric power, there was a very broad network of telegraph wires, and the telegraph operators often would know that when there's space weather, when there's aurora, they could disconnect their telegraph from the battery and still communicate, because the aurora would produce currents in the telegraph wire that was essentially the same as the battery itself. So they would actually use an aurora-powered telegraph for a while, and in some extreme cases there were stories, anecdotal stories, of arcing between the wire in the telegraph room itself and some other equipment, starting papers on fire and things like that. It's very, very difficult for us to know exactly how big that storm was, because there were a few ground magnetometers measuring the magnetic field, but the calibrations were different and things like that. They do estimate that it was a very, very large storm, but our estimates are highly uncertain. The piece in the Washington Post will make comparisons to that and say, well, based on what they saw, this particular CME did not hit Earth, so we were lucky, but it did hit a spacecraft called Stereo, which is on the other side of the sun, and so they were able to measure the impact at that spacecraft, and it was a very, very big event. There are some who will say it was an extreme event. Others will say, well, it was about like the last really big event we had in 2003. It's very, very difficult to know exactly. as you saw in my presentation, I think there was a little bit of sensationalism going on, and you had to, they made some assumptions and said, well, if everything lined up perfectly, you might have had this kind of situation. But I am not worried, and I am not losing sleep over the possibility of a major space weather storm.
Okay, thanks. Brian from Colorado wants to know if you were able to predict when the next K9 storm will be.
Good question. Yes, I would love to be able to say yes, but right now I can tell you only through statistics. K9 storms are fairly infrequent. We get 1, 2, maybe 3 a solar cycle, but as we said, this is a low solar cycle. On the other hand, the last time we had a solar cycle of this size, which was in 1921, just after that solar cycle maximum in 1922, we had one of the biggest space weather events in one of the top 10 space weather events. So even small solar cycles can have big events. We are on the declining side of a solar cycle, so we've reached the maximum and we're now headed downward, and this is the time when you do have the biggest space weather storms, believe it or not. So we are in a right position, and even though the solar cycle is small, it doesn't mean we won't have big storms, but exactly predicting when it might occur is very, very challenging and not something we have mastered yet.
And Brian, following up on that question, asked, would it be possible for us to gather energy from an aurora?
That's an interesting question, and there was a prominent senator from Alaska who started to try and get funding for aurora research by claiming that we were going to get energy from the aurora. It's not stable enough, it's not static enough, nor is there enough power. The aurora and the ground-induced, the geomagnetic storm-induced currents that we see on our power lines, in a sense, it's noise. It causes fluctuations, but it doesn't give you enough power to really generate the kind of power we need to power whole cities. Like I said, you can get enough to arc across and burn some papers on a desk, but not to really generate that kind of electricity.
I'm getting a bunch of questions wanting to know, Rodney, if you are a ham radio operator yourself.
No, I'm not. I do know a number of ham radio operators, and one of our forecasters, Rob Steenberg, is very much a ham radio operator, and so I rely entirely on his expertise when it comes to that subject matter.
Okay, well, Mary in Wisconsin writes that her husband is a ham radio operator, and what her husband would like to know is the bounces or skips that occur on CB radios, are they caused by CMEs? And she's finding this presentation very, very informative. So
yeah, so the CB radio is a little bit different frequency than the ham radio, but it has the same impact. You are still often being able to reflect off the ionosphere. I think CB is supposed to be line of sight more than reflected, but again, when the ionosphere is very enhanced due to space weather and from CMEs, radio propagation and the multi-bounce radio path becomes very complicated. We still are not able to forecast exactly where you will be able to hear each other. We can give you estimates, and there are a number of websites that you can log on to and put your location in and put your friend or your receiver's location in, and they will tell you if there's good conditions to communicate or not.
And another ham operator, Tom, is writing in and wants to know that in a severe event, will any of his antennas or radios be destroyed? Would it be prudent to store radio in a metal box with a wire antenna, the box sitting on wooden blocks, he asks?
No, I don't think there's enough radiative energy from the aurora. I think, again, it's going to be not the space weather or the aurora that causes the problem, but if there's a problem on your electric power grid, if your power grid is somehow affected and you have power outages, that will be a problem. And again, you're more likely most often to have that sort of effect from a lightning storm. I know lightning is very bad on electronic equipment, so if you protect yourself from lightning, you're probably well protected from any kind of event that the space weather would do, and the space weather would mostly affect your electric power grid, not the antennas or the radio itself.
Thanks. Richard in Tennessee writes about the rock underneath where he lives. He says there's a massive plutonic rock under the land he owns. Would that have any bearing on attracting or repelling a view of the aurora there in Tennessee? So does where you stand, does that do anything to I would doubt it does, but we'll ask you that question.
Yeah, no. I mean, the rock under Tennessee is part of this in the northeast part of the country. The conductivity of that rock is very much part of why that part of the world is susceptible to the electric power grid issues. But the aurora itself is not going to come and go based on where that conductivity is. And it will come over Tennessee just as reliably, whether or not that the rock itself was there or not. On the other hand, if you go further down into the into the mantle and into the liquid core of the Earth, where the electric or the magnetic field of Earth is actually generated, yes, that will start. If you were to modify that, they talk about the shifting of the poles and the reversing of the poles. That will have a big impact on where the aurora is, and we don't even know what will happen. But they say that the poles are moving more rapidly, and that there's sometime in the next few thousand years we may see a pole reversal. And at that point, yes, you would be able to see the aurora from wherever the pole was at that moment. So if the pole was somewhere on the equator, you would see the aurora at the equator.
Okay, Jim in Missouri wants to know, what are the dangers to life from, I assume, from the solar flares and the protons and stuff that you mentioned? So would it cause cancer? What are the effects, I guess, of this exposure?
Yeah, really from and it's mostly the astronauts outside the atmosphere. The impacts are going to be the radiation. And that radiation does get into, it penetrates deep into the body and will break apart your DNA molecules and cause mutations. And that's really the problem that people are most concerned about. And there is a significant risk to astronauts. There is a very, very slight risk, perhaps, to passengers and crew in aircraft. But I will caution people that you should not worry about it, because worrying about it is probably a higher risk. They've done statistical studies on pilots. We've been flying aircraft at high latitudes and high altitudes for decades, and if you look at the statistics of what those people later in their lives end up dying of, there is not a significant increase in the kinds of deaths associated with radiation. So there really isn't a statistically significant increase in risk, even if you're a pilot. So we try and tell people not to worry about it, although it's still something. Radiation is always something that people are concerned with, and it's scary because you can't see it.
Okay, Michael writes in and wants to know, he said, some recent news suggests solar storms can increase lightning activity. Any ideas about that?
Yeah, okay, we're going. Yes, there are studies that show that you can actually find correlations between space weather and terrestrial weather. I think over the course of a solar cycle, that and where weather and climate overlap, that's the question. The solar cycle will have an effect on climate, and it will affect where the low pressure systems travel and the storm tracks and things like that. That's something that's fairly well documented. And so yes, your local weather may change based on the solar cycle, but I don't know. People have looked for and tried to identify a connection between, say, a big storm, a single space weather storm, and the weather immediately following, and it's been very hard for people to find statistically relevant correlations. I did read about the lightning, and there have been others that associate with the Earth's electric field and things like that, and there are possibilities. It may in fact be true, but I have not seen that sort of the smoking gun type of evidence that says, yes, this is the direct correlation and this is how it works.
Michael writes in and he wants to know, is there any significant difference between the northern and the southern aurora? So the ones you see in the North Pole and the ones that are on the South Pole.
The biggest difference between the North and the South Pole is the offset between the geomagnetic pole and the geographic pole. Turns out the southern geomagnetic pole is even further from the geographic pole than it is in the north, and so that oval is further off shifted. So if you were able to go to the southern hemisphere and look for aurora, there would be a place where you would be even further towards the equator and still be able to see the aurora. Of course, the aurora oval itself in the south is mostly over the Arctic Ocean, so or the Antarctic Ocean, whatever. it's very difficult to get to see the aurora because most of the generally inhabited areas, South America and the southern part of Africa, or even Australia or Tasmania, those places are still quite far equatorward of where the aurora is. But one of the things that's interesting, and people have done a lot of work trying to study this because it helps explain some of the physics of the aurora, is that the aurora in the south and the aurora in the north are mirrors of each other, right down to some of the subtle details. You can actually see brightening and dimming of the aurora at both hemispheres simultaneously, indicating that the process of acceleration is occurring somewhere out along the magnetic field line, and it's occurring to both hemispheres at once. So in effect, they are identical, or mirror images of each other.
Okay, Eddie from Pennsylvania, always concerned about, or folks are concerned about government cuts, and have or will government cuts negatively impact space environment satellite programs? Any news on that? It's always a battle to maintain funding from a federal source, and you know, as the federal dollars are scrutinized more and more, it's a challenge to keep those terrestrial weather and space weather sensors are indeed both under scrutiny. The GOES program, which is NOAA's big geosynchronous satellite program for weather and for space weather, continuously gets sort of scrutinized by Congress. The Polar Satellite Program, which was formerly the POSE program, is now being replaced by JPSS. In fact, on that satellite program, the space weather sensors were removed because of budget issues. So yes, there are times when the space weather sensors are sacrificed because of budget cuts. On the same side, a lot of people are putting up. We are now able to get lots of new and exciting data from NASA, and even from, for instance, the Iridium satellite phone company is providing some really unique space weather data. So we have other sources that pick up and fill in some of those gaps. But it's always challenging to justify and maintain some of those data sources for operations. Ronnie, do you have time for a couple more?
Sure.
Okay, we'll try to get a couple more questions in here. Felix writes, and he says he's listened to propagation reports on WWV for many years as a ham radio operator and has never understood the Boulder A index. Do you know what that is?
Yes.
And could you explain it briefly?
I don't know if I can explain it. I know what it is. So A index and the K index are both geomagnetic indices. They're generally related. The A index is the K index is a log scale. The A index is a linear scale. So you can look at the Boulder A or the Boulder K, and they will essentially tell you the same thing, which is a disturbance. What is the local disturbance of the geomagnetic field? And the reason we've got a Boulder K index is very historic. Back long before, back in the 20, 30, 40 years ago, it was much more difficult to get data from around the world in real time. And when I say real time, the Weather Service considers real time to be anything less than 30 minutes old. We need our data within 3 seconds. And so real time is very, very short for space weather. And the only way to do that was to have your own magnetometer in your own backyard. And so that's the Boulder magnetometer, because that's where the Boulder Space Weather Prediction Center was. And for historic reasons, we continue to broadcast the Boulder A index as an index of the local magnetic field near Boulder. And the assumption is that that will be then representative of what the geomagnetic disturbance is around the world. We know that that's not a very good correlation, and that those assumptions are not very good, and we're moving away from having an index based on one station to these global indices like the AP, which is the planetary A index, or the KP, which is the planetary K index. Those are indices measured with many stations around the world and capture that geomagnetic activity more completely, even if it won't be biased by having a measurement at only one station. I hope that helps explain it. Please send me an email and I'll get a more detailed answer from the forecasters if you want to know more.
Ronnie, I got another quick one for you. Other stars out there that are in other galaxies, they probably have solar flares. And so are we affected by any of these other stars out there, or is it too far away for us to be?
That's a very good question. There are events on other stars that have measurable Again, I don't think we have enough data. We've only been looking out there at these other stars for, maybe 100 years, and these events may be something that occur only a few thousand years. But you can have massive flare-like events from a star that sends out X-rays or even, higher energy particles. And yes, there may be an effect here on Earth. Certainly, we've measured them with our, we're looking at the sun and looking for solar flares, and those same sensors are sensitive to these stellar events, and so we've been able to measure them. Now, whether or not they will affect us, that's a whole other question. I think there's speculation that, yes, maybe if one of the stars that was very, very close to us were to have some sort of massive explosion, there could be an effect here on Earth, but again, I don't even know that we know what that would look like, or certainly we couldn't forecast it.
Okay, we're going to take two more questions here to wrap things up today. Steve writes, where does the Air Force SESS fit in, if you're familiar with that? I'm not. I don't know what that acronym is.
Yeah, I've heard the acronym, but I can't remember which one it is. The space environments, it might...
Steve, if you want to elaborate, just type that in, and we'll come back to that question next. And here's another one here. Scott writes, is the strength of the Earth's magnetic field, if it is decreasing, as some say, what will be the effect on solar radiation influx in the borealis and so forth?
That's a good question, and I think people speculate and try and model that impact. If you were to just take a very simplistic approach, you would say if you reduce the Earth's magnetic field, then you would actually open things up to more of the solar wind particles that could penetrate deeper towards the Earth. But I think that the Earth's atmosphere itself is actually a very strong protector, and so even if it were more particles getting to the upper atmosphere, it might change the ionosphere, but it probably won't affect things down here on Earth. Now, there is one other theory that people have used about why some planets have atmospheres and some don't, and very often there's a correlation between that planet's magnetic field. So if our magnetic field were to go away for millions and millions and millions of years, there's a possibility that the solar wind would slowly scrub the atmosphere from our planet. But that's highly... I can't imagine how that would happen. As long as we've got a liquid core inside our planet, we will have a magnetic field, and that magnetic field will help prevent the solar wind from penetrating and scrubbing away our atmosphere.
Okay, well, here's the last question for the day. This one looks pretty interesting. Back in the 1950s, Janice writes, they were watching television in western Kansas, and all of a sudden they received a TV station from Rio de Janeiro. Was there a large solar event at that time, or could that happen to, boy, you wouldn't really need cable if you had that.
Yeah, no, that, again, this
was the World Cup, who knows? No.
Right. Well, not many people get their television over the old-fashioned ways with antennas anymore. And yes, during space weather events, the ionosphere can set up multiple layers. It's not just one layer, but can have several layers, and you can get what's called radio wave ducting, where basically it's like a funnel. You can get radio waves that kind of get reflected back and forth between a few layers, and they can be ducted halfway around the world. So yes, those kinds of things can happen, and I know the ham radio operators always challenge themselves to see how far away they can get their signals from, and sometimes during certain conditions they can get signals from around the other side of the world.
Well, Rodney, thank you so much for taking time out of your busy day to be with us today. This was great stuff. All of us here at the Climate Center appreciate your doing this, and we also appreciate you being a CoCoRaHS observer as well. So thank you for your reports from up there. So we'll be in contact with you to get some more information for our website. If we get that, we'll get that movie URL and some other stuff. And folks, we'll be posting that here within the next week, as well as Rodney's slides from today, and also today's broadcast. Well, for everyone out there, please join us for our next CoCoRaHS WxTalk webinar, and that's going to be in a few weeks on Thursday, August 14th. If you've ever watched CSI on TV, you'll be interested in something like this. We'll be on Weather CSI, the Forensics of Meteorology, and that'll feature CoCoRaHS Georgia Regional Coordinator and Certified Consulting Meteorologist Pam Knox out of the University of Georgia. So we'll have that up on our website where you guys can sign up for that shortly. Again, before signing off today, please take the survey that'll pop up on your screen. And so until next time, this is Henry Regis for the rest of the Climate Center and CoCoRaHS team saying goodbye for now and have a great afternoon.